So imagine you just tap a button on your phone, right? You're transferring 800 rupees to a friend.
Hmm.
The screen loads, the money leaves your account, but in the exact millisecond before it actually hits your friend's account, the server handling the transaction just catches fire.
Just total power loss.
Exactly. Total power loss. Where does the money go? I mean, is it just floating in some digital void forever?
It's a terrifying thought, honestly.
It really is. And today on the deep dive, we are pulling back the curtain on the invisible architecture that prevents that exact nightmare from happening to you. We're exploring a stack of source material on transaction management and query processing.
Right, getting into the real nuts and bolts.
Yeah, our mission today is to figure out exactly how these massive databases handle, like, millions of concurrent actions without losing a single byte of your data or just grinding to a complete halt.
It really is a highly orchestrated ecosystem beneath the surface. I mean, we tend to view an action like sending that 800 rupees as one singular event.
Yeah, like one click.
Exactly, one click. But the database does not see it that way at all. It sees a transaction, which is actually a sequence of microscopic, really low-level tasks.
Right, because there's no magic teleportation of money, right? The system has to physically do the math.
Precisely. To the database, that single human click initiates a multi-step physical process. First, it performs a read operation.
Okay, so what does that look like?
Well, it navigates to your account, let's call it account X, reads the old balance from the physical hard drive, and pulls that data into a temporary buffer.
Like in the system's active RAM.
Yes, exactly. Only then does the CPU actually do the math, subtracting the 800 rupees. And next comes a write operation.
Taking it out of the RAM.
Right, taking that new balance from the temporary buffer and writing it permanently back to account X on the disk. And after all of that, it have to repeat the entire read, calculate, and write sequence for your friend's account Y.
Okay, let's unpack this for a second, because breaking it down into those distinct physical steps is exactly what makes that server fire scenario so terrifying.
Oh, absolutely.
If the power cuts out after the system writes the new lower balance to my account, but before it even opens the buffer for my friend's account, my 800 rupees is just missing, the math doesn't balance anymore.
And that right there is the core vulnerability of any digital system. To prevent that, database architects enforce a strictly rigid set of rules over every single transaction.
Right.
You'll see this referred to in the sources as the ACD properties, ACID.
Right, AC. So the A stands for atomicity. And I was thinking about this like a relay race, actually.
Okay, a relay race. How so?
Well, if you're passing a baton to the next runner and the baton gets dropped, the database doesn't just say, oh, well, keep running without it. Instead, time literally rewinds. The race is erased as if the starting gun was never even fired, and the runners are magically back at the start line.
That is a great analogy. And that is the absolute rule of atomicity. It's the all or nothing principle.
All or nothing.
Right. A transaction is treated as one indivisible unit. It cannot occur partially. It either runs to absolute completion, which we call a commit, making all changes permanent and visible, or it aborts.
So if a failure happens...
If a failure happens at any microsecond before that commit, the system rolls back every single change. There is no midway point where the money leaves your account but doesn't arrive at the destination. It is all, or it is strictly nothing.
Which is incredibly reassuring for my bank account, frankly. And then the C in ACID stands for consistency, right? Meaning the database has to follow the laws of physics, essentially.
Quite literally, yes. Consistency ensures that the database transitions from one valid state to another, strictly enforcing all defined integrity constraints.
So the math has to add up.
Exactly.
Yeah.
In our banking example, the total value of funds across both accounts combined must be identical before the transaction begins and after it completes. The universe's fundamental rules, as defined by the database administrator, of course cannot be broken by a transaction.
Okay, I follow the logic for one transaction, but this raises a practical question for me regarding the ACID isolation.
Yes, isolation.
Yeah, because if I'm transferring 800 rupees, that's fine. But what if 1 million people are transferring money, buying concert tickets, and, updating their profiles at the exact same millisecond?
The traffic jam scenario.
Right. If you and I are both frantically clicking to buy the exact same seat on an airplane, how does the system not trip over itself and sell the seat twice?
So the concurrency control subsystem steps in here to enforce isolation. The rule is that while multiple transactions are executing simultaneously in the background, they must execute as if they were the only transaction in the entire system.
Wait, they think they're alone?
Yes. They are entirely blind to one another's intermediate, uncommitted changes.
How does that physically work, though? I mean, it can't just pretend the traffic jam isn't there.
It manages the traffic through a system of locks. Right. If transaction 1, say, your request for the airplane seat accesses that specific row of data to read and modify it, the database places a lock on that data item.
Oh, I see.
So transaction 2, my request for the exact same seat, arrives a microsecond later. It hits that lock. My transaction is forced to wait in a queue until your transaction either commits or aborts and releases the lock.
Wow.
We never interact with the data at the same time.
So it literally barricades that specific piece of data from the rest of the world until the job is done.
Precisely. And the final property, the D, is durability.
Right, durability.
This is the guarantee that once a transaction does commit, its updates are permanently etched into the system, even if the server immediately loses power.
So even if the server catches fire right after the commit.
Exactly. The recovery subsystem ensures the new data is safely written to non-volatile memory, meaning physical disk storage, not just the temporary RAM buffer. Once committed, the effects are never lost.
So we have this impenetrable, rewindable ACD vault. But a vault is useless if we don't know what's happening inside of it, right? It's a process, not an instant flash.
Right, it takes time.
So how does the database actually track a transaction's journey to make sure it's following all these rules?
The system maps the journey using specific states. Every transaction has a defined life cycle. The moment it begins reading data into the active memory and doing the math, it is in the active state.
So it's working on the scratch pad.
Yes, the scratch pad. And once it executes its final operational step, say, calculating the final balance for account Y, it advances to a state called partially committed.
Partially committed. That implies there's still a chance it could fail, right?
A significant chance, actually. The math is done in the temporary buffer, but the database recovery system still has to run its final security checks.
Oh, to make sure everything is legal.
Exactly. It verifies that all integrity constraints are met and that the hardware is prepared to write the data to the non-volatile disk if any of those checks fail.
Like a rule violation.
A rule violation, a deadlocked queue, a hardware glitch. The transaction immediately drops into the failed state.
And if it hits the failed state, it triggers that atomicity rule we talked about, the rewind button.
Exactly right. A failed transaction can never proceed. The recovery manager takes over and systematically rolls back every write operation, scrubbing the temporary buffers and returning the database to its exact original state.
Wow.
And once the rewind is fully complete, the transaction enters the aborted state.
So it's dead. But what happens next? Does the database just throw its hands up and tell me my transfer failed?
Not necessarily. From the aborted state, the system makes a binary choice. If the failure was due to a temporary internal issue like hitting a lock because someone else was updating the account at the same time, the system will silently restart the transaction automatically.
Oh, so you as the user would never even know it failed the first time.
Exactly. It happens in milliseconds.
Yeah.
However, if the failure was due to a severe logical error, like trying to transfer money from an account that doesn't exist, it will kill the transaction and return an error message to you.
But if all the checks pass during that partially committed phase?
Then it writes the data to the disk and enters the final committed state. The transaction is permanently established.
Okay, so we've built this incredible architecture to protect the data while it moves. But, and this is what I was wondering, a vault is useless if it takes the system 10 years to find the money inside.
Fair point.
Before it can even lock the data, it has to find it. How does the system take a messy human request and turn it into a hyper-efficient search mission in the first place? Handing a query to a database feels like handing a scribbled dinner order to a highly critical chef.
That's a great way to look at query processing, honestly. Step 1 of that process is the parser.
The parser?
Right. When you submit a high-level SQL query, it's written in a syntax close to human language. But the machine hardware doesn't understand SQL. The parser acts as a translator, converting your SQL into low-level relational algebra.
So the chef is looking at my scribbled order. What is the parser actually translating and checking?
During the parse call, it runs 3 distinct checks. The first 2 are straightforward. A syntax check to ensure you didn't misspell a command like typing form instead of from.
Done that a million times.
We all have. And then a semantic check to verify that the tables and columns you are asking for actually exist in the database schema. But the third check is where the heavy computational lifting begins. It's called the shared pool check.
What exactly is a shared pool?
Every time a query is parsed, the database assigns it a unique mathematical hash code. The parser checks the shared pool, which is a dedicated area of memory, to see if this exact hash code already exists from a previous request.
Wait, let me push back on that. Why does a database need to remember old hash codes? Like, if I'm asking for today's bank balance, why does it care if someone asked a similar question yesterday?
Because calculating how to answer a question is incredibly resource intensive. If the parser doesn't find the hash code, it performs what is called a hard parse.
A hard parse.
Yes, it has to send the query through a gauntlet of complex optimization algorithms to figure out the most efficient physical path to retrieve your data from the hard drive.
It has to invent the recipe from scratch.
Exactly. And inventing that recipe burns massive amounts of CPU time and memory. But if the hash code does exist in the shared pool, the database performs a soft parse.
So it skips the hard part.
It completely bypasses the optimization steps,
Yeah.
retrieves the previously calculated execution plan, and jumps straight to the execution engine. It already knows the recipe, so it just starts cooking.
That makes perfect sense. So let's say we get a totally fresh query, a hard parse. The database has to figure out the recipe. How does it find the absolute best way to fetch the data without wasting a ton of time and resources?
This is the domain of step 2, the optimizer. You can think of this as the master tactician of the database.
Okay.
The optimizer pulls various potential execution plans stored in the database catalog. Its singular goal is to evaluate every possible path to your data and select the plan with the lowest computational cost.
I want to understand the physical reality of this, though. Let's say I'm looking for one specific employee in a massive database. How does the optimizer plan that search? Does it just read the list from top to bottom?
It evaluates that option, yes. Reading from top to bottom is called a linear search. The system scans every single record, block by physical block, testing if it satisfies your condition.
But if there are millions of records, isn't that incredibly slow?
It is the absolute slowest algorithm available. And we have to think about the physical hardware here. Data is stored on physical disks that spin, read by a mechanical arm.
Oh, right, the actual moving parts.
Yes. Accessing a block of data requires the arm to physically move a mechanical seek. If the system has to do a linear search, and the data blocks aren't scored right next to each other in a contiguous line, that mechanical arm is darting all over the disk. A mechanical action is millions of times slower than an electronic calculation in RAM.
So the optimizer's entire job is basically trying to avoid moving that physical disk arm. What's the faster alternative, then?
The alternative is utilizing index scans. An index is a highly organized data structure, like a map, that provides an access path to the data.
Kind of like the index at the back of a textbook. Instead of reading the whole book to find a mention of George Washington, you just look at the index, see he's on page 42, and flip straight there.
Exactly. And the optimizer has several index types to choose from. If your query is looking for an exact match on a totally unique value, like one specific employee ID, it uses a primary index.
Okay.
This gives the database the exact physical address of that single record on the disk. One mechanical seek, and you have your data.
Okay, but what if my search isn't totally unique? What if I say, find everyone who works in the marketing department? Hundreds of people could have that job title.
Then the optimizer evaluates using a secondary index, which allows the database to fetch multiple records based on a non-key attribute.
Right.
But where it gets truly fascinating is when you ask for a range of data. What if you want to find every employee who makes between 50,000 and 80,000 rupees?
A linear search would have to read every single salary in the entire company to check if it falls in that bracket.
Right, which would cause a massive bottleneck. Instead, for range queries, the database relies on complex ordered structures, most commonly a B-plus tree index.
A B-plus tree. I've seen that term in the source material. How does a B-plus tree actually work?
Well, imagine a massive corporate hierarchy. You start at the top, the root node, and navigate down through branches based on values, narrowing your search until you hit the bottom layer, called the leaf node.
Like the rank and file employees at the bottom?
Exactly. In a B-plus tree, all the actual pointers to the physical data are stored only in these bottom leaf nodes. And here is the genius part. Every leaf node is linked directly to the one next to it, like a daisy chain.
Oh, I see. So if I want salaries between 50K and 80K, the database navigates down the tree once to find the 50K mark, and instead of going back up to the top to search for 51K, it just slides laterally along that daisy chain at the bottom, 51, 52, 53, until it hits 80K.
Yes, it slides perfectly across the contiguous values, ignoring the millions of irrelevant records and stopping the moment it exceeds your target. The optimizer calculates that this lateral slide requires vastly fewer disk arm movements than any other method.
It's brilliantly lazy. It figures out how to do the absolute minimum amount of physical work.
That's optimization in a nutshell.
But pulling a list from one table is relatively straightforward. What if my query requires mashing massive tables together? Like, take the table of 10,000 employees, combine it with a table of 10,000 payroll records, match everyone up, and sort them.
You've just described the heaviest lifting a database can perform: joins and sorting. Because these operations combine multiple data sets, the threat of uncontrolled disk accesses is exponential.
It could just crash.
Easily. The optimizer has to evaluate 4 primary join algorithms to prevent the system from crashing under its own weight.
Let's walk through them. If the database is inherently lazy, what's the brute force method it's trying to avoid?
The brute force method is the nested loop join. It consists of an outer loop and an inner loop.
Okay.
The database takes the first record from table A, say, employee number 1, keeps its virtual finger on that row, and then reads through every single record in table B looking for a match. Once finished, it moves to employee number 2 and reads the entirety of table B again.
Wait, let me do the math on that. If I have 10,000 employees and 10,000 payroll records, 10,000 times 10,000 is 100 million. It has to perform 100 million physical reads just to join 2 moderately sized lists.
Exactly. Which, as you can imagine, is computationally devastating if the data is sitting on a physical disk.
Yeah, the arm would be moving forever.
Right. To mitigate this, the optimizer might upgrade to an index nested loop join. If table B has an index, the database doesn't have to scan the whole table for every employee. It just pings the index.
Which saves millions of reads. But if joining is that expensive, I assume the database tries to organize the data before mashing it together. Like, if you just sorted both lists by employee ID first, you could just match them up side by side, right?
You have just independently invented the sort-merge join.
Hey, look at that.
And you are correct, it is highly efficient. If both tables are pre-sorted by their common attribute, the database can just read down both lists simultaneously.
Like zipping up a jacket. As long as the teeth on both sides are lined up in order, the slider just glides up in one smooth, linear motion.
And just like a zipper, if one tooth is out of order, the whole mechanism jams. That is why a sort-merge join strictly requires that sorting phase first.
Makes sense.
Alternatively, the optimizer might choose a hash join. This involves taking the smaller table and running it through a mathematical hash function to build a temporary, highly organized table in the active memory.
Okay, so it preps it in the RAM.
Right. Then it scans the larger table, hashing its values to instantly find matching buckets in the memory. It's incredibly fast, provided you have enough RAM to hold the temporary hash table.
So memory size is a huge constraint there. And what about that sorting phase? When I click a column header to sort my bank transactions by date, how does it do that without freezing my computer?
Sorting depends entirely on dataset size. If the dataset is small enough to fit entirely inside the active RAM, the database uses lightning-fast, in-memory algorithms like quicksort.
Right.
But if you are asking to sort a massive dataset that drastically exceeds the system's memory limits, it has to rely on an external merge sort.
Because it can't hold all the cards in its hands at once.
Exactly. It has to pull chunks of data from the disk, sorts those small chunks in RAM, write the sorted chunks back to the disk, and then carefully merge those chunks together.
That sounds like a lot of work.
It is an intensive dance of moving data back and forth. This is why the optimizer will desperately try to use a B+ tree index to pull the data out already sorted, avoiding a dedicated sorting operation entirely.
Okay, we've covered an insane amount of ground here. We have linear searches, B+ tree daisy chains, nested loops that can cause 100 million reads, hash joins relying on RAM, external merge sorts chunking data back and forth. How does the system finally decide? Who makes the final call on which path to take?
The final call is made through cost-based optimization. The optimizer generates a query execution plan.
Okay, an execution plan.
First, it maps out a logical plan based on the relational algebra the parser created. Then it translates that into multiple potential physical plans.
So it maps out all the possible routes to the destination, like picking a driving route.
Yes. One physical plan might suggest a full linear scan and a nested loop. Another plan might suggest using a B+ tree index and a sort and merge join.
Right.
And then the database acts as a ruthless, highly calculating accountant. It assigns a mathematical cost to every single step of every plan.
Like calculating the gas and tolls for the road trip.
Exactly. It estimates the disk I/O cost, meaning exactly how many times it will have to physically move that mechanical hard drive arm. It estimates the CPU cost, how much processing time the calculations will take. And it estimates memory usage, how much active RAM it needs to hold temporary hash tables or sorting chunks.
It's predicting the future toll of the operation.
Completely. It weighs all those hardware variables, calculates a final score for every single route, selects the absolute lowest cost physical plan, and only then does it hand the instructions over to the execution engine to actually fetch your data.
That is just wild. I mean, we've gone from a simple tap on a smartphone screen, translated by a parser into algebra, evaluated by a ruthlessly lazy, cost-based optimizer trying to save milliseconds of mechanical disk arm movement, navigated through the daisy-chained leaf nodes of a B-plus tree.
All in the blink of an eye.
Yeah. All while being surrounded by an impenetrable, rewindable ASIC vault that ensures not a single cent of your 800 rupees is lost if a server catches fire. It really is an invisible miracle of architecture.
It is a microscopic war room. The system calculates millions of physical variables and logical constraints in a fraction of a millisecond. Entirely so a human being never has to wait an extra second for a web page to load or worry that their money disappeared into the void.
So to you, our listener, the next time you type a search and get a result instantly, or you see that transfer successful screen on your banking app, take a second to appreciate the sheer mechanical and computational choreography that just happened in the background.
It's worth appreciating for sure.
But I want to leave you with a final thought to mull over today. Databases can instantly evaluate the cost of every possible path, weighing memory, time, and physical effort before taking a single step. Imagine if human decision-making had a built-in, cost-based optimizer for our daily choices. Would we make perfect decisions, or would we just get stuck in the parsing phase forever?
A fascinating question.
Thanks for diving deep with us today.